I'm Alfred Spector, and I'm the moderator. I have to my immediate right, your left, Hoelzle, which I didn't quite pronounce right, but it will get better as time goes on because I practice machine learning also. Rob Pike, Ed Lazowska, and Jeannette Wing. So we're going to talk about this, computing at scale. Now what I wrote was, and what we wrote, the frontiers of computer science are being increasingly impacted by computing at very large scale. That is, on a very large scale computing systems, perhaps in the cloud with possibly significant dependence on large scale data sets and or systems with shared use by vast populations. This panel will explore the potential opportunities and challenges in computer science research in this space. Jeannette.
Am I on?
You're on.
Okay, do I really need this? Okay, well we were told that we were given 3 minutes each. So I have 3 main points to make. The first one is actually just to share with you a serious interest that the National Science Foundation has in what we're calling data-intensive computing. And the recognition of why this is important, it probably shouldn't surprise any of you here, but I'll just mention to you this observation that there's this convergence in trends that make this sort of a tipping point, if you will, for our field. So first of all, we are drowning in data, and I need not tell you how much data we're drowning in, but I do want to mention a few facts here, like CERN's Large Hadron Collider will be generating 15 petabytes of data a year once it starts working. There's an international data corporation says by 2011 we'll have generated 1.8 zettabytes of data, digital data. Zettabyte is 1 followed by 21 zeros. Okay? So we're talking about a lot of data. George Gilder, a techno-future evangelist, predicts by 2015 that the US internet will be US internet traffic will be around 1 zettabyte annually. So a lot of data. So trend number 1, we're drowning in data. Trend number 2 is, as was mentioned earlier, a lot of areas within computer science are taking what we would call a data-driven approach. So we're seeing it in graphics, animation, machine learning, speech translation, even computational biology. So that's trend number 2. Trend number 3 is storage is cheap. Trend number 4 is a growth in huge data centers. Trend number 5 is data is in the cloud, it's not on your machine. And finally, I think one of the things that's really going to enable the computing community, the research community especially, is that there's now easier access and programmability of these large cluster machines, if you will, whether it's renting through Amazon or using the Google and IBM cluster provided via NSF or your own huggable cluster. So that, and then finally, of course, part of that trend is the programmability, meaning the open source Hadoop, for instance, that Yahoo's providing. So those are all trends that are converging and basically saying, you know, we have to pay attention to this data stuff. So that's the first point I wanted to make, and that leads me into just describing a little bit about what this Google and IBM software services data cluster is all about and how we really are together with the National Science Foundation and Google and IBM are basically throwing a challenge to the entire community, the computer science community, the scientific community in general, saying, you know, now that we have provided the general academic community access to this large cluster, what can you do with it? And there are actually, I think, scientific, technical, and societal questions, research challenges that we could be asking. So for instance, from a technical challenge, of course, there's just how do you operate these things in as automatic a manner as possible? What kind of reliability and automatic configuration management can you actually run these sorts of things? And from an applications or a societal point of view, you can imagine, well, the challenge is, you know, well, we know we can do search, but is that all we can do? So we're really interested to see how the academic community responds to now that the fact you can't make the excuse if we don't have access to this. Okay, so the other thing I wanted to say is that this software and services that Google and IBM are providing through NSF to all of you is really part of, or in fact a seed of, this larger effort that I mentioned before, the Data Intensive Computing Program. And yes, if you're following your NSF email, you should have seen the solicitation that came out on the Data Intensive Computing Crosscut, and the CLUE, Cluster Exploratory Program, was really meant to seed that. The other point I usually make in the same breath, although maybe it's not pertinent to this audience, is that we welcome other corporations to participate in the Cluster Exploratory. The last thing I wanted to say about the Google and IBM partnership with NSF is that we broke new ground at NSF doing this. This is very different, and it was very exciting for me to kind of be the one to shake up NSF and turn it on its head and say, you know, they're not providing a physical instrument, and no, I have no clue of where it is, but it doesn't matter because it's in the cloud. And the director looking at me and like getting this worried look, you know, I can't touch it. No, you can't touch it. Okay, so anyway, besides all the lawyer stuff that we had to go through, the last point I wanted to make, and this is really to the computer science community. You might think that you don't have access to data, but there's tons of data out there. And where is it? It's with the scientists. The scientists are drowning in data. So for instance, my favorite example now is the geosciences. What do they want to do? They have this grand ambition. They want to model the Earth, from the inner core to the Earth's surface to the sun, and all the layers in between, and all the systems interacting, from the hydrosphere, the cryosphere, the atmosphere, the sphere just under the crust, and even the biosphere, the biodiversity, because any perturbation in one of those systems might have an effect in some other system that's obviously, you can't, you know, the Earth is the Earth, you can't separate it. And moreover, they actually have some specific goals for the near term, which is to be able to predict climate on the 10 to 15-year scale, because that's what matters to us as citizens. That's what matters to your local politician who has to make a decision about, do we recycle bags or do we ban plastic bags? Because a decision that he makes or she makes now will affect the citizenry in our lifespan. And so that's why it's not, you know, do climate modeling and what is the world going to be like in 100 years. It's what is it going to be like in 10 or 15 years. And they want to be able to predict climate on a regional scale, because again, it's what affects us, what affects my neighborhood, what affects, you know, where my children go to school. So that's just one example. The scientists are producing and generating more data than they can store. They are throwing away data. And I can tell you more about that after Rob Pike speaks.
Okay, I'm Ed Lazowska. I will be closer to 3 minutes than Jeannette. I should have set that as my goal. I made a big mistake. I'm going to be a bit redundant, I'm afraid, but let me just highlight 3 things at a minute apiece. One is the educational thrust, which you've heard a lot about from various people. At this summit last year, Christoph Basilia and some other people from the University of Washington and Google described the course that we taught at UW and described the original Google IBM initiative, and it's come a long distance since then. 6 months ago, NSF, as you've heard, joined the partnership through the CLUE program and now the Data Intensive Computing Program. Christoph is speaking in one of the breakouts at 4:15 this afternoon. So if you're interested in educational aspects, you should find him and sit at that table. I think what's important is that this isn't vocational training. I mean, we love it when these courses send students to Google. It's a great place to work. But the truth is students need to learn how to think about solving these very, very large-scale data problems. And we haven't been teaching our students to do that, and we are now. And that's a real change. And it fits anywhere in the curriculum. It can fit into your systems courses or your programming language courses or almost anywhere. It can be a freestanding course, but it's something that's got to get into the curriculum, and it's valuable because it's a new way of thinking. It's not just a new programming language, a new programming paradigm. It's a new way of, new style of problem solving to tackle. Someone mentioned earlier that we just concluded a 3-day workshop that the National Science Foundation and Google sponsored for a set of 40 faculty members who were trying to learn how to teach this stuff. And the material from that is all on a website. For those of you who don't trust Google, if you go to lazowska.cs.washington.edu/Google, I have a bunch of links to things that might be relevant. You can probably find them all with your favorite search engine, but they're there as well. Again, we had participants there from not just Google, but Yahoo, Amazon. We had sort of curricular material presented. It was 50% presentations and 50% labs for the teachers, and there's tons of material there that you could use to move this into the curriculum. The second thing I want to talk about is I'm involved in this outfit called the Computing Community Consortium, whose goal, it's an NSF-sponsored initiative, is to try and get all of us to think about sort of longer-range research challenges. And one thing we did last March under the leadership of Randy Bryant, who's here also somewhere there, was to sponsor something we called the Big Data Computing Study Group. And Randy organized 2 workshops in March down at Yahoo. One was called the Hadoop Summit, and one was called the Data Intensive Scalable Computing Symposium. The Hadoop Summit was originally scheduled for a little conference room at Hadoop, and we managed to have to move it to the San Jose Convention Center, where it had more than 350 attendees. The goal there was to build a sort of community of practice of people using Hadoop. And the goal of the DISC Symposium was to build a community of practice of researchers interested in scalable computing problems. And it should be clear that this impacts system design research, programming language research, application support research, and applications themselves. There's tons of work for us to do. And an important element there is to listen to Jeff Dean tomorrow, who Alfred challenged to put together a talk for us on what Google thinks the pressing systems and languages and application support challenges are. These are things for us to work on. Google doesn't pretend that it's answered those questions at any level. Finally, at the University of Washington, we've recently created something we call the eScience Institute. And there are 2 goals of this. Let me tell you what my fear has been. It's that the previous generation of computational science, that is simulation-oriented computational science, was a tiny niche. Every campus had a couple chemists, a couple physicists, a couple astronomers. The new computational science is this data-centered science. Every science is flipping from data poor to data rich, just as Jeannette was talking about. I've been working for a couple of years with some oceanographers at the University of Washington, and the project there is to put 2,000 kilometers of fiber optic cable on the Juan de Fuca Plate off the coast of Washington and Oregon and British Columbia, and hang thousands of chemical and physical and biological sensors off that grid and stream data back. The oceans are responsible for a huge amount of the environment that we experience, oxygen, CO2 exchange, and things like that. And we know nothing about them because we don't have any data. Oceanography is an expeditionary science. You go out in a ship, you drop instruments, you come back. This is going to transform oceanography. Universities are going to cease to be competitive if they don't bring computer scientists and disciplinary scientists together and figure out how to do the semi-automated knowledge discovery in this mountain of data, as well as the sensor networks and stuff like that.
All right, I'm going to be even closer to 3 minutes. I have just a single point, but it has 3 sub-points. To me, the clusters in large-scale computing is actually about collaboration, and pretty much about collaboration only, because if you just set up one of these things, or if you want to construct one, you actually need not, computer science, like computer architects, all right? Or you don't need, system administrators. You need, mechanical engineers to figure out the building and the cooling and the power, right? You need hardware engineer to do the servers and the racks and et cetera, right? Networking hardware for that part, operating systems, middleware, the applications on top, right? The networking, it's the whole stack. And if you ignore any of these and also how these interact, you're going to have a sometimes strongly inferior solution. So just to construct one is a lot of collaboration. And then as Ed and Jeannette actually alluded to, I think the key use of these clusters is in collaboration in several areas. One could be the pure computer science part, right? So if you want to understand how the cluster actually works and how you can operate it sort of hands-off, that's a collaboration between people who have much more operational thinking and then people who have much more algorithmic thinking, and you got to put the two together, right? And you probably can't solve it with either half. Or similarly, in an interdisciplinary way across disciplines, right? Let's say you do, go to one of these people who have lots of data, right? Biology or geo, satellite images and so on and so on. I think this is where the big breakthroughs are going to happen because you have to process that data, but the processing itself is difficult enough, and then the science on the geo or bio or whatever area is just as difficult. And one of the mistakes that I think that we've made in the past, and I've seen this myself as a faculty member, is when we do interdisciplinary research and you work with a biologist, people evaluate, we computer scientists evaluate ourselves by what we accomplish in computer science. I found this cool new string matching kind of thing. But actually what matters is what impact you made on biology, right? Do we understand, genetics better or something like that, right? And so I would encourage people to, think about that when you see an opportunity and really try to work on problems that matter in the fields that you're collaborating with, right? Because that will automatically produce good computer science and good, whatever the other science is. So I think my 3 minutes are up. Bob.
All right. I'll try to be even briefer, but it'll be easy because I've sort of been covered already. But I'm going to change encouragement into an admonishment. I think academic computer science is in danger of not being part of this story at all. Computing at scale is something that so far has not been done in academia. And I don't see that changing very soon unless you listen carefully to what has been said and what I'm going to say too, I think. One of the problems, of course, is you need equipment. That's not really the problem, although it's too much spoken about as being the problem. There's also educational issues and things like that, but that's not really what's hard. The thing is that computing at scale is just an empty idea if you don't have something you're going to do with it. You can build all the equipment you want, you can run all the software you want, but if all of it does is generate computer science papers, you're not doing anything except advancing your own careers. And I think that's bad. The CS community just isn't looking hard enough at what applications can be done. But if you look at high energy physics, bioinformatics, geology, things like that, there are problems out there that need to be solved, and the CS community is quite simply letting them down. Google is part of a collaboration called the Large Synoptic Survey Telescope. It's an astronomy project that'll generate of order 20 or 30 petabytes, several terabytes per night. There's a huge data processing problem, there's a huge data analysis problem, data mining problem, accessibility problem, and computer science as a community has so far delivered essentially nothing to help them. And as a result, they're going off and they're rolling their own. And they're probably not going to do a great job, but they're going to do the best job they can with the tools they have available. Now, this is actually an interesting exception to prove the rule in the LSST, because as a result of them canvassing for ideas, Michael Stonebreaker has decided to try to help them and build a special high-speed distributed data system for analyzing the kind of stuff they want to do. But I think it just proves my point, because in order to get funding for that, he had to go outside, basically make a startup and ask for private funding from companies like Yahoo, eBay, and Google. And I think that that is an example of what I'm talking about. It's not working within the academic community itself. So the NSF, it's okay. The NSF has to step up to the plate. I think they haven't, thank you. I don't think they've done enough to support interdisciplinary research. I think they talk the talk, but they don't walk the walk. They don't make the money available if you have a true interdisciplinary community. And the CS community, in turn, has to decide that it's valid, as Urs said, to do science in areas other than computing if along the way you generate good science as a whole. Big science has the budget, it has the equipment, and it has the problems, and CS should be there and helping.
Yeah, so I'd like to say something about the comment. Now, this is actually a constructive response, not a defensive response. And that is a program that I did forget to talk about was the Cyber-Enabled Discovery and Innovation, which speaks exactly about collaborations and interdisciplinary research, where the requirement for a successful project is advances in both computer science and some other discipline. And it was the biggest program that the National Science Foundation put out this year. It's foundation-wide. Every single director in office in the foundation is participating. SAIS is the lead. And this program was for all of you. And I have to admit that I wish I saw more of you sort of proposing in diverse and interesting ways, because I worked hard to help create this program for all of you. And I think this is really speaking to what Rob Pike, I think, was admonishing the community for. And in defensive remark, the National Science Foundation actually is putting money into this and is trying to encourage interdisciplinary collaborative research, but it's up to the PIs to actually respond.
So Ed, what's CCC going to do to catalyze our community to be involved as a partner in interdisciplinary efforts rather than a consultant to interdisciplinary efforts?
I think all you can do is point to examples. And there are lots of examples out there, and it seems to me there are plenty of computing research topics in everything that's been talked about. If you look at Jim Gray's trajectory over the last 5 years of his life, it was realizing that for better or for worse, we design systems badly enough that whenever you add a decimal order of magnitude in 1 or 2 dimensions, you've got a new research problem. And that's what scale is about. So it seems to me that there's plenty of what we consider to be computer science research if we can just get over our insecurity about being people's handmaidens.
I would say, though, that you're still focusing on the computer science problems, and of course you're a computer scientist, so that's okay. But even just doing a really good job that doesn't generate a computer science paper but helps scientists do breakthrough research, that's valid research too, and should be done.
So we have a bunch of questions here that are given. We'll generate some questions for ourselves, but we must show that we are responsive to all of you. So the first question is an interesting one. I'm not sure how much we can get into it here. We'll take that one. Google and others have taken revolutionary steps in how computing is delivered with desktop quality apps running within browsers. However, programming these apps is challenging, and the apps typically cannot leverage all the resources available locally. How do we see the web browser evolving to support hybrid desktop mobile cloud? So Rob or Ors, do you want to take that one?
I can just give my opinion. I don't have any insight. I think that the browser is becoming the operating system, and they're just sort of co-evolving. And at some point, you could even argue that you need something analogous to a JavaScript native operating system for which the browser is the shell, and that's sort of the end of it. Of course, all of the parameters in that are bogus, but the concept is roughly right, and there's even things along that line being developed by people like Dan Ingalls. The balance of power between the cloud and the browser and the computer is kind of funny, but I think it's roughly right. I think the structure is viable for scale. But the support environment, particularly executing within the browser, which is a crock on a disaster, on a mistake, is just not suitable. And without a complete reset, which is very hard to do, I don't think we're going to be able to do a lot better than the trajectory we're on.
I think it's actually an opportunity for academia to make a contribution because the upside is large and the bar isn't very high. I think it's clear that nobody really wants to use Ajax, right? But it's the best thing that actually works out there, right? And so everyone does use it because you really have no choice. As Rob says, it's not going to be easy to replace this, tomorrow with something else. But eventually it's going to happen, and when it's going to happen, it is because there is a different model that makes it much easier to not just program the client, but also orchestrate the computation sort of between, and the data between the client and the cloud, and which is very cumbersome today because you have to do sort of everything. We're, in the meantime, kind of doing things along the side. So, for example, Google Gears lets you, store things locally in a browser accessible and reasonably safe way. But I think that's a short-term. I mean, that API may persist, but it should be implemented really for something other than JavaScript. And I'm sure longer term it will, but in the short term, you got to make, programmatic steps. But I think there's a huge opportunity there. So if you have great ideas in this space, write some Ajax applications, and it tells you what the problems are, and then, write them again in your better system.
On the health question, on this one, I'll apply editorial comment to say that privacy issues are not really the topic of this panel, but there is a Google Health talk which is coming either next, I think it's next, or else it's tomorrow, and that would be a perfect question for that panel. So let me just lead that one to that panel. So the next one was, what do Google insiders think? And I'd like to change that to what do members of the panel think, that tomorrow's undergrads need to know about large-scale computing. So Ed, do you want to start with that one?
Let's see, I think when Christoph motivated the creation of this course 2 years ago, it was based on the observation that the students he interviewed, the hundreds of students he interviewed at Google, were great at coming up with algorithms and data structures for handling small-scale problems, and were paralyzed when it came to algorithms and data structures for large-scale problems. And it seems to me that we're more and more dealing with large-scale problems, and people simply need experience in thinking at that sort of scale, the scale of thousands of processors and terabytes of data. That's what we're trying to provide, and then all the rest of the stuff.
Anyone else?
Everything you said is right, but I'd like to add that there's another approach to it, which is to instead find ways to make it so you don't have to think about that. That you can, if you can find a way to make the problem more manageable by appropriate programming paradigms or layers or abstractions or languages, then that's great too. I mean, one of the reasons we can function at the scale we do is that we found tools like MapReduce and Sawzall and things like that that make the programmer not have to think about scale because the underlying layers take care of it. And there needs to be more work done on that stuff as well, particularly for problems that are not as easily sliceable up as MapReduce solutions tend to have.
Right. I don't think anyone at Google believes MapReduce is the solution for all problems. It's essentially a batch processing technology, and it's highly valuable for that. But I'm sure Jeff will talk tomorrow about the challenges you face when you're dealing with real-time interactive computing that requires vast parallelism. That's another topic. All right. So, what are the three biggest challenges in operating large-scale clusters? Or I don't think anyone knows that better than you do, so you'll have to take it.
So there's many different answers, and instead of giving you the three biggest challenges, I'll give you the biggest challenge in three different ways. No, seriously. So there's really, a cluster is many things to many people, right? Ideally, to the application programmer, right, to the end user, quote unquote, it is just a pool of resources, and you don't have to deal with failure and things magically scale. It's kind of like you're an app engine user, and here's your app, and suddenly your input goes up by a factor of 1,000, but except for your bill going up, things work, right? And so the biggest challenge is, how do you make that illusion actually true, right? How do we build middleware systems infrastructure that to the programmer removes as much of the complexity as is possible, right? That's a huge challenge. We have a few answers in a few areas, but we don't have the answers at all, right? So that's the first one. The second one is, if you actually operate the cluster, how do you control costs, right? The energy is a big portion there. Construction costs, capital expense. How do you really physically operate things? The data center industry has been sort of dormant for the last 30 years in the sense that your typical data center design today is the same that it was in 1968, and is hugely inefficient, right? I mean, hugely inefficient, right? In a typical data center, after you account for all the losses, including the losses in your computer itself, and you look at the real productive electrons consumed, that's typically 1/4 of the power that comes in from the electricity company, right? So you have 75% going to waste and 25% going to the actual computation, and clearly that's, this ratio should be very different. That's a big challenge. I think the third one is what we talked about before. If you want to view the end user not as a scientist, but actually as a consumer, how do you really orchestrate sort of the division of labor between the cloud, i.e. the data center, the large-scale cluster, and where your user is, right? Maybe they're on a mobile device, right? Maybe they have a desktop. Maybe you have lots of storage locally. Maybe they don't have much storage at all locally. Again, right, it's something that I think has been thought about for 25 years in different contexts, but hasn't been real. And now it's really becoming real as broadband becomes reasonably pervasive even on mobile devices, so that you can actually have some communication and not die kind of right away. So I think those are, in each of these areas, the biggest challenge. And there's probably a few more.
Expanding on your last point, I'd like to say that I was at a National Academy meeting about a year ago, and there I commented that there has to be a change in the way the problem solving is done structurally, because if you want to do research in this area or even use these tools in this area, you can't be expected to build a data center, fund all that stuff. It's just not going to work. And I think we're going to see a change in the way that computing gets done, so that commercial companies, Google's, Yahoo's, eBay's of the world, Microsoft, they start providing services analogous to what Amazon is doing, but on a much bigger scale, such that they're just part of the infrastructure that is supported. And we need to find a way to make those infrastructure elements available at a convenient way that the entire community can use it and depend on them as sort of fundamental infrastructure, instead of things you build with a small Beowulf cluster in a rack in your university department.
Jeannette, it's a little bit early for you to answer this from an NSF perspective, but thinking through, say, 5 years out, what do you think the alternatives are, or the options, or what's the space going to look like for NSF-related activities in supporting computationally intensive cluster-based tasks?
Well, first of all, I want to just share with you that the other ADs and the other science, am I on?
Yeah.
Other science directorates recognize that where their problem lies right now is in the data, and also the software, I should mention. It's not supercomputers anymore. It's not compute processing power. It's not throw more processors at it. They're saying to me, Jeannette, we've got all this data, help us. And they understand that it'll be new data structures or data representation or new algorithms or new programming models and new languages and sort of new bread and butter computer science that they need, and it's not big iron anymore. I mean, of course, there will be big iron always. So I think because, at the highest levels, the scientists are crying out actually for our help and our creativity and our contributions in fundamental ways. I think I can imagine in 10 years that, if we had the money to do all this, that's where it would be different from, one or two supercomputers, in the country or something like that. But I'm speculating.
So I just wanted to take off on something Rob said, and that is the pragmatic version of what are the problems in running large-scale clusters is we shouldn't be doing it, right? And how many of you have actually used Amazon Web Services? I mean, some, okay? It's quite remarkable. Dave Patterson, his group wrote a paper using Amazon Web Services to experiment up to the 1,000 processor level a month ago. And Dave has this slide where he points out that the remarkable thing is that 1,000 processors for 1 day costs as much as one processor for 1,000 days. Okay, that's a revolutionary sort of new equation for computing. So for a modest number of thousands of bucks, his group was able to conduct 1,000 processor experiments, which just would have been infeasible doing it themselves. The New York Times used Amazon Web Services for a couple $100 to convert their entire archive, digitize their entire archive. And Werner Vogels shows this slide of Animoto's EC2 instance usage. Has anyone not seen that? Okay. Animoto is this little company. They do something that only your kids and mine would appreciate. You give them an MP3 and a bunch of JPEGs, and they produce a slideshow that's syncopated to the music. And they, like many new companies these days, don't have any computers. All right? They use Amazon Web Services for this. So the graph is Amazon EC2 instances consumed by Animoto, and it's bopping. By the way, it takes about 6 minutes of computing to do one of these things, okay? So it bops along at about 50 instances, okay, up and down over a 10-day period. And on this past April 15th, they rolled out a Facebook app, all right? And they went from 50 to roughly 3,500 instances in a day and a half. Right? And you don't do that by calling the Dell salesman and saying, I'd like another 3,400 of these things running by Tuesday, right? So this is just incredibly powerful, and Microsoft will be providing a comparable service, and Google is providing one, and Google and IBM and Yahoo have provided capabilities to the university community. So we got to get out of the business of thinking that we have to be able to physically touch these things in order to do interesting work and interesting research on them.
Let's see if there's a question from a table. Good. Microphone for you first here. All right.
So It's not as if, though, that these issues that you're raising are new. We've had high-performance computing for a long, long time, and NSF has spent countless dollars on high-performance computing, and a lot of those dollars have gone into what we all know and know as grid computing. So I would like to hear from the panel what your opinion is of what went wrong. So we've spent so much money, and we've been duly admonished by Rob for very good reasons. Not much has come out of that effort. What were the mistakes of the grid funding effort? What should we do to avoid that kind of a failure in the future?
So I'll try to answer that so that Jeannette has it. And it was before Jeanette's time, right? So remember that. But so I think two things. I'm not a huge HPC fan because I never found it that interesting, but it's not exactly a failure, right? But one of the differences really is that the factors involved today are very different, right? What really was sort of a national scale $100 million program, just 10 years ago, you can basically do with your pocket money almost today, right? And so this kind of computation is available to everyone, right? Including the data. And in fact, more data is available to everyone. The second thing is that HPC worked really great for very closely coupled parallelism kind of things. And one of the, but that made the box more expensive, right? And the model of the box was you use it all with your big, weather simulation, right? And everyone else waits, right? And then you move off and, the next job comes, right? Here, I think the success is going to be based on having this pool of machines, be that at Amazon or somewhere else, there's multiple users at the same time. Plus, you don't need the closely coupled parallelism, right? It's a lot more data mining, streaming through much larger data sets, things like that. And plus, you got to have a way of tolerating failure, right? If you look at the HPC clusters and their average uptime, right, it was measured in hours, right? Not days, basically, right? So typically tens of hours. And then one of these umpteen thousand processes would fail, right? And fortunately, you had checkpointed your thing, right, 3 hours before, so you can, fix it, go back, start, right? But that leads to pretty poor utilization. And it's not the fault of the vendor, right? If you actually look at, the failure, the uptime of a cluster, even if your component is 6 nines reliability, which is almost impossible to do, right? At a large-scale cluster, you get 2 nines, right? 1% failure chance, right? And then you get the hours of uptime, right? And so in the model where you don't need the whole cluster closely coupled, you can deal with much cheaper hardware. You can get much more bang for the buck, to a point where it's really affordable for almost anyone, right? Amazon is making money at, the numbers that Ed was quoting, right? And Dave Patterson is using, right? So this is reasonably close to the real cost of computation. It's not a subsidized kind of thing. And that, I think, is what really changes the game, right? I think everyone who has petabytes of data can afford to process them if they knew how, right? And if the processing facilities were provided somehow. But I'm sure that is the easy part, right? So I agree with Ed. I wouldn't worry about the physical thing. I mean, I think it's a super interesting field, and so for some subset of us, yes, we will worry about it. But that's not the problem that the sort of we as a discipline face.
Yep. Question.
So yeah, it's a bit
You're on. You're on.
slightly different question here. Hardware vendors are scratching their heads to understand what is the best way to design the servers for these big clusters. One problem is that we don't have the workloads. We don't understand what the workloads. I'm sure that Google has a lot of information on this stuff. Is there a way to make this information public? What kind of data patterns, what kind of components in the computer are the most stressed? This sort of thing.
So great question, Joseph. I know where you're coming from. I'm tempted to say, it doesn't matter because that's not the first line problem. At a cluster level, for example, how you deal with failure, right, at the software layers above is going to have a bigger impact on the actual performance you get out. How you deal with networking, right, given that either you spend a lot of money for a completely non-oversubscribed, non-blocking kind of network, or you deal with some form of QoS, right? How do you orchestrate the computations per se, right? If you look at the MapReduce, as an example, it's not limited by the performance of the machine. It's limited by, or it's, you can get much bigger speed ups if you do the orchestration of the computation better, right? Rather than the memory fetch better, so to speak, right? Because when you have really large data sets, you're going to spend a fair amount of effort moving it around, right? And not just, you know, like in the traditional HPC things, it was really, you know, gigaflops and very regular computations and sort of things like that. So here, your best workload is, you know, something equivalent to, you know, GCC or, you know, general sort of integerish, for us, integerish workload, lots of memory, lots of I/O. But I think the node matters much less than the cluster.
All right, so there's a question here which we'll abstract from. We have 5 more minutes. Is that, can we use that much time, everyone? 10 more? Okay. All right. Many of the physical and biological science are facing a massive influx of data. So processing, storing, and querying these data is becoming a major challenge. I'd like to just augment it as what are the Google technologies and what are the research challenges more broadly that are applicable. So Rob, do you want to take a poke at this initially?
I can start. I think it's interesting that Hadoop has caught on. We weren't able to disentangle MapReduce enough from our code base to open source it, and I think that's a kind of a shame. But it's interesting that Hadoop has caught on so much because, and it's caught on not because it is the right solution to all these problems, but because it solves some subset so well and easily that it can really catch on. I think the Google technologies that I've seen internally, we talk about, that are most important are actually mostly in the area of fault tolerance, how it's handled and how it's hidden. When you have, as Urs said, when you get enough machines together, it doesn't matter how good they are, they're going to break. You're going to have some of them break and your job's going to go down. And when I first came to Google, one of the first sort of amazing insights that I learned here, just from watching how things worked, is that there's a sort of equation that develops out of this. If you're at scale, then you have hardware that's going to break no matter how good the hardware is. That means your software has to deal with that. And once your software is dealing with that, it doesn't matter how good the hardware is anymore, so you can buy crap and use it and it'll work. And in some sense, MapReduce is the apotheosis of that weird argument, but it works really well. And I think it works not because the programming model is perfect. It works very well, but it's not perfect. I think its fundamental thing is how it hides underneath its layer all of the fault tolerance things that bedevil any attempt to use large clusters. And I think that's the essence of its brilliance, and not the algorithm per se. And I think a lot of in my dealings with the LSST, I'm struggled to try to get them to understand that fault tolerance is a thing they should be thinking about first, not last. And it's a lesson that they know I'm hammering into them, but they're not quite letting me hammer hard enough. So that's kind of the point I'd like to make there. Do you have anything, Urs?
Oh, perfect answer.
Ed, any comment on research topics in this space, or Jeannette? All right. So there's another Google Health question. I'd love to talk about this because I'm involved in this on a regular basis, and again, we'll cover that at the breakout on that. Suppose we measure efficiency by the amount of energy expended to answer a query. There is both an interactive component and a constant component to the energy expended. How has Google's efficiency evolved over the past, say, 5 years?
So we don't track, joule per query. We look at watts or QPS per query, so queries per second. QPS per watt. So per watt of computation, how many queries can you answer? The total amount of energy per query has risen over that period because the web has gotten much bigger, and so the workload for one query has gone up by a lot, right? Easily a factor of 10, right? Probably more, closer to a factor of 100. The energy efficiency has gotten quite a bit better. I would speculate a factor of 2, maybe a little bit more, something like that. Well, probably more like, if you include the software optimizations, actually probably more. Okay, 5 years, actually, I would say, low 10, factor of 10, right? Just where we've gotten much more efficient. As the index grew, we had to understand how it works better. And so per document searched, we've gotten much more efficient in terms of energy spent. And then the hardware is a factor of 2, probably.
I'd also like to add that the hardware community has not done enough towards energy efficiency in computing. There's just some amazing data, that, some of which we've actually published. Louise in the back there did this paper a while back. But if you look at what the ratio is between the power that the computer uses and the power that the computer extracts for useful work, it's way, way too bad. And for instance, an idling computer uses far too much power, even though it's doing absolutely nothing. And I think as a research topic to help data center builders, I think Urs would agree that it'd be really nice if the computer architects found a way to control the power budgets in their computers vastly better than they do now. And I mean vastly.
Questions from the audience? Anyone here? Yep, over this side.
Yeah. Is it on? I want to switch back to the starting point, which was the change in science from all the data availability and the need for computing at scale. How does data-centered science change the nature of science? Think about how we learned to be scientists. We got great value from having intimate contact with the data and the data collection mechanisms. For example, we understand the uncertainties in the research process. As we move to data-driven science, software intervenes between the scientist and the data. How is that going to affect the overall judgment process that scientists need to bring to bear in order to formulate good questions? So how do we help young scientists develop the judgment skills at that high level to be great scientists when automation is in the way between them and the data and the phenomena in the world?
And software bugs, right? Yeah, I mean, I wonder how many papers are going to be published about data that's wrong. I mean, the data is correct, but the bug in between the data and the result made the result invalid. I don't know.
As a former physicist, I think I have something slightly relevant to say here. I was actually a physicist who became a computer person because I was doing computational physics, and at the time, eventually I had to leave the physics field because nobody believed the computations I was doing were real. There were simulations that were getting 7 and 8 significant digits that in the end agreed with experiment, but nonetheless I couldn't get people to believe that that was real physics going on. That was more years ago than I care to recount, but nowadays that attitude is completely gone. Science is data-driven, people trust computers to give answers, but from the point of view of a working scientist, the thing that matters is the scientific training is what matters more than the computational training. When a scientist gets a number by calculation or by experiment or by computation, if the number isn't right, the scientist should have the training, the understanding, and the scientific skill to understand that it's not right. And I think computers can help at scale by providing secondary algorithms to do data validation, data injection, test quality stuff, things like that. But fundamentally, it comes down to just scientific training, I think, that would dominate.
So I don't have an answer, but I think this is a really interesting question that I hadn't thought much about. It seems to me that one can argue that the level of integration of physical things, for example, electronic devices, keeps kids these days from understanding how things work, right? You can't take it apart and put it back together. There's no batteries and light bulbs and knife switches, and you're arguing that the same thing is true for the conduct of experiments if you're using data mining and machine learning to extract patterns from data. So it's a great point. I think there's a direct analogy.
Well, there's data. There is data on this. It's not simply speculation, and it plays out in the history of cockpit automation as one example where pilots lost that judgment, and we had to reinvent training programs. And it wasn't just data validation, new ways to trust the automation. It was new ways to think about what you were accomplishing in the world, and training that judgment required a whole new set of techniques in a highly computing-intensive world.
Yeah, I would agree with you there, and I think agreeing with the other panelists. And in fact, we as computer scientists actually know, where software problems can actually lead to wrong conclusions if we don't have that kind of judgment. And in the other sciences, that is why they still do rely on real physical instruments and putting sensors in the ground, whether they're in the Antarctic or buried somewhere in the U.S. And they go and physically go there and take measurements and try to validate the experiments that they do in the lab. It's a very expensive way of doing science.
Okay, question over here.
So a couple of you, especially Rob Pike, admonished us computer people to do more disciplinary science and to count advances in disciplinary science as things to aspire to. I'm very sympathetic to that goal, but I think you weren't really addressing the complexity of actually realizing that. And I think the central complexity of realizing that is that the people in this room, well, by and large, we don't do much. We read email and we talk to people. But if anything's going to happen, it has to be done by graduate students. And I think that's the nub of the problem, because, for a computer science graduate student to concentrate in their 5 years in producing results in a disciplinary science, they're shooting themselves in the foot. And I would tell them honestly that I think it would be great for the world if they were doing that, but they're shooting themselves in the foot in terms of having a future career in computer science. And so I wonder if you had thoughts on how to solve that problem.
It's all about the money. If the community changes such that funding is available, either through scientific disciplines offering money for computational endeavor, or by the NSF explicitly encouraging and continue to encourage this kind of thing, then by definition, it'll happen. You're not in charge of what gets done directly, but very indirectly, you're very important to what the graduate students work on, and you're a key part of getting money, right? If the money flows into your lab to develop a collaborative effort with some scientists on this project, and what comes out of that is a graduate student who's good at collaboration and understands and there's a money pool that continues to develop in that area, it's going to happen. Now, I'm not making light of it. I'm not saying this is a simple problem. But I do believe there's a mistake in your logic, and that is that it's a fundamental problem in money, not in what people's careers look like, that's going to change this.
Okay.
So this will be the final question.
So one of the things that's drawn me to respond is because we keep making the same kind of fundamental computer science mistakes over and over again. So what Rob Pike said about collaborations as peers is important. And I just heard about the problem of confirming the kinds of hypotheses that we use our machinery to create. And if we don't get the point that if we don't work as collaborators and peers and provide ways of interpreting the hypothesis space we manage for all these scientists, we won't get out of this loop that Rob's admonishing us to get out of. We need to work, and there's a discipline called artificial intelligence that studies the notion of capturing metadata and reasoning about it. Right? So, there are ways and directions to go, and they don't always come from the things that I've heard so far. There's lots to be done.
Well, I think that's a good last statement. There's lots to be done. So I think we want to thank our panelists. Thank you all.